I'd like to give you some tips on a tried and true method for determining the mass flow rate of a substance into or out of an open system when you're not given that value. So what we did was we just identified the continuity equation for an open system. Let's see, it says the rate at which the mass of the control surface changes, dmdt of the control volume, uh, equals the sum of the mass flows in minus the sum of the mass flows out. It's something you can remember in your head. It's not a formula that you need to fall back on, but in many cases, in your homework problems, quiz, test problems, and certainly also in engineering practice, it's a little unusual sometimes that you're given the mass flow rate. Maybe pretty common in homework and test problems, but not quite so much in engineering practice. I want to give you some tips on how you might estimate or calculate the mass flow rate. So let's look at some examples. There's that continuity equation. And want to talk about, we're going to purely talk about steady state situations. In other words, all of these flows depicted here, water coming out of a PVC pipe, water coming out of a steel or iron pipe, the exhaust gas flow rate from two fighter jet engines, complete with afterburners burning. For example, we're going to focus purely on steady flow. Those flows are not changing in time. They're doing the same thing they're doing the same thing at breakfast time as they are at lunchtime. And so for this particular sketch, I'm going to start m.1 equals m.2 for my little open system example, and we're just going to say that equals m dot. Okay, since they're both equal to each other, I've got one inlet and one outlet. You're going to be working on many problems like these for the rest of the course and beyond. Okay, so and typically there will be situations where you're not given the value for the mass flow rate m dot. Your book does a superb job of developing from first principles in section 4.1.2, evaluating the mass flow rate. And I'm kind of going to sort of a bottom line and giving you details of the bottom line. So this expression 4.3 is m dot equals this integral. I'm going to plop that down on the next slide, but then the book goes from that first principle expression down to m dot equals rho AV, or m dot equals AV divided by B, V, little v, that's specific volume. Oh, rho, that's density. Some details about this. Okay. And so back to your textbook, the fundamental principle here is m dot is the integral over the surface area of the pipe or duct or whatever you're trying to analyze. This is the area integral over an area, a surface, equals rho times velocity times dA. That's the way that you're integrating. So you're integrating over incremental areas, looking at each little rho and each little velocity. You're doing an integral. Okay, well, let's see. How do we get from here down to something that we're going to use in our class? And so, does a miracle occur? No, here's what we do. We say, and this is a classic sketch or image to illustrate this, the density. You'll need to agree with me that the density of water, no matter where you sampled this water flowing out of the pipe, the density would be the same. So there's no variations in the fluid's density depending on where you are in the flow. So that's going to be constant. Now, another thing, I'm going to say a little bit more about velocity here in just a second. For those of you that have taken or are taking fluid mechanics, you might argue with this, but I'm just going to say it, that we could calculate sort of an average velocity of the flow in this water. Now, we could do some scientific measurements, and we would see that in nearly all of the flow, except for at the surface of the pipe. In nearly all of the flow, the velocity coming out of that pipe is pretty well constant. But I'm going to say we're going to say we've got nearly uniform velocity across that area, and then the integral over the area. So with those sort of things said, we get m dot. Well, if that's constant, we pull it out of the integral. If velocity is constant over the area, we pull it out of the integral. So all we have to do is integrate dA. Well, that's just A, the area. So that's how we get m dot equals rho AV. Now, I have grouped AV together for a reason, and I'll disclose that here in just a second. But this is where reviewing your textbook is extremely valuable. The textbook wording wraps a lot of words around how to get from here to here. Remember that rho is density. Capital V here is velocity. A is area. Okay. This is something we can work with. As engineers, we can work with this m dot equals rho AV thing to determine the mass flow rate. So that's sort of the big conclusion here. Okay, some details, some details about why I grouped together A times V. The area times the velocity is called the volumetric flow rate. And when you have homework problems and you see the words, the volumetric flow rate is 3 cubic meters per second, for example, that's disclosing what the product A times V is. So let's look at the units of A times V, the volumetric flow rate. Okay, in SI, A times V, it's going to have unit check. Meters squared will be your area. Meters per second will be your velocity. So the volumetric flow rate would be cubic meters per second. Okay, let's look at some fundamental units for English, AV. Feet squared would be the units that you need to use for area. Feet per second, of course, is going to be the basic units for velocity. And so we do the math, and we've got cubic feet per second. Got it. And that's a good textbook approach. Now let's go down to engineering practice and things that we read, things we can read off a nameplate of a compressor or other type of situations. A times V is going to be, well, area would be square feet. And in many cases, the velocity is expressed in feet per minute. And so do you see that if we do our unit check, we've got feet cubed per minute, and in many nameplates and in common jargon, we call that CFM, cubic feet per minute. And so if you have certain engineering problems, even a homework problem perhaps in English, and it'll say the volumetric flow rate is 100 CFM, that's what that means, cubic feet per minute. The velocity V. So in our modeling, we consider some folks that are taking or have taken fluid mechanics will do a little argumentation about this, but just agree with me that for our purposes, we're going to say that the velocity in meters per second or feet per second, it's considered to be a uniform velocity across the cross section of the flow. Now, so for those who will argue, no, the velocity is different. So in the real world, we know that the highest velocity is in the middle of the pipe. Here, maybe not quite so much here, but we do know that there is a no slip condition between fluids and solid surfaces. So we know at the surface of the control volumes, there's a no slip condition, zero velocity. And so just kind of agree that in thermoclass, what we do is we say that we have determined by hook or crook a uniform constant velocity across the cross section. So in most cases, we use what we call the average velocity of the exit flows or entrance flows to open systems. So recognize that V in this class would be considered the average flow velocity through the pipe or the duct. Okay, let's see, figuring out density or specific volume. So remember, m dot is rho AV, or m dot is AV divided by little v. Either one is fine, because Rho density is the reciprocal of specific volume. So you can do whatever your choice is. You work with specific volume, work with density, either way. How would you get those? Well, it depends on your problem, doesn't it? Ideal gas, ideal gas. Ideal gas equation of state. Rho is P over RT. That's the way I get rho. Or V, specific volume. It's RT over P. Same ideal gas equation of state. So if your flow is an ideal gas, boom, you got it. How about a phase change substance? How about steam or refrigerant? Or even a propane flow, a flow of propane gas going into your gas grill. Well, you're going to need to go to your thermodynamic property tables and figure out specific volume using tabular values, and rho is simply the reciprocal of 1 over the specific volume. So hard and fast rules for rho, for little v, no, it depends on your substance. So let's recap. AV, so the AV, the product of area times velocity is called the volumetric flow rate. Got to commit that to memory. Just showed m dot equals rho AV, or m dot equals AV divided by little v. And that's, of course, associated with these classic images of outflows from open systems. The next thing I want to cover in Chapter 4 is what we call steady state, steady flow. So we're not going to crunch any numbers in the next video, but I really want you to get a good understanding of what does steady state, steady flow process, what is a steady state, steady flow process? I want to devote a few minutes to that. So I hope these things help, and keep up with your homework assignments.